Good afternoon, ladies and gentlemen. It's really wonderful to see so many people here today in this historical venue, the Royal Institutions of Great Britain. Today, we are honored to have Professor Steve Furber to give this last lecture of this academic year. Professor Furber is a distinguished computer scientist of this country and the world. During the last 40 years, he has made enormous contributions to the computer science and the industry. And he is the principal designer of the BBC Micro and also the principal designer of the ARM chip. So his work now is benefiting all of us now. So in all of your pocket, you at least have one chip that's made by Steve. In 2004, he initiated the Brainlight computer design in Manchester. Since then, he led the world in this fast-growing development. Today, Steve will present to us his pioneering work on a brain-like computer systems called Spinnaker. At Imperial, we are in fact building on Steve's work in various areas, and we have researchers explore the chip, the Spinnaker technology to optimize big data processing, for example. In fact, in August, the Data Science Institute will host the 2015 Brain Informatics Conference, International Conference in Imperial College. And you can actually see some brochures and also the information about the conference outside. Hope we will see you also in this conference. I hope you will enjoy this talk and you'll find Steve's talk today informative and inspiring. I will now hand over to Axel. He is a distinguished journalist from Reuters, who will kindly agree to chair this rest of the events and actually host the interview. Thank you very much.
Thank you very much indeed. I'll keep this very, very brief because I know we want to hear from Steve this afternoon. That's why you're all here. But I can't tell you what a pleasant change this is for me to be hosting something like this rather than a session on why or whether Greece is going to leave the Eurozone or whether the US is going to raise interest rates, which is what I usually do. You're probably wondering actually why someone like me with a history degree rather than a degree in electrical engineering or computing or maths is hosting a session with Steve Furber. Well, I was reliably and politely informed that a layperson brings somewhat of a refreshing perspective to an event like this. I think what they were really trying to say is, look, you, Axel, can ask all the really dumb questions, and you guys can ask all the really clever questions. But that is the way we want to run this afternoon. We're going to hear from Steve for about half an hour or so, and then we thought it would be nice to do a Q&A session. I'll kick us off with some questions, and then please do have a think about what you want to ask him. We've got an hour. Well, we'll have half an hour for Q&A, so do make the most of that, because it's not usually how he does sessions like this one. So, Building Brains, Learning from Data is the title of the discussion, how computers can learn from data. We're of course seeing more and more computers used in interactive sensory roles, but how far can we take this? This is hopefully what we'll learn about this afternoon. Will we be able to build brains that truly learn from data? Will AI ever be so advanced that machines don't need us anymore? What really are the prospects for strong AI? And could it be as dangerous, as big a threat as some, including, as I'm sure you're all aware, Stephen Hawking and Elon Musk fear? Those are some of the questions we'll be asking Steve this afternoon. There's a long list of awards and distinguished achievements, but I will mention that last year he was made a distinguished fellow at the British Computer Society, recognizing his contribution to the IT profession and industry. There was one quote when I was just doing my own research into this that did stick with me, and I'll read that out to you now. It was from a guy called Mark Weiser who worked at Xerox, and he said this back in the 90s: the most profound technologies are those that disappear. They weave themselves into the fabric of everyday life until they are indistinguishable from it. Of course, computers have to a large extent done that. We've got to wonder whether in 10 years' time we'll be saying the same thing about robots. Without further ado, though, Professor Steve Furber.
Well, thank you for that introduction, Axel and Nike. I've got half an hour to give you a quick top-level overview of my perspectives on the topic of the day. The talk will be principally about building brains with a little bit of learning from data, because we haven't really yet got the capability to build systems that learn from data as effectively as brains do. Maybe that will change. To start the talk, here's a quote from 200 years ago. Earlier in the year, I gave the BCS Lovelace lecture, and as part of that, I did a little bit of homework on Ada Lovelace, who was an assistant to Charles Babbage, who is very famous in computing circles for designing mechanical computers that never quite got built. And Ada wrote programs for these. But in the context of my work, Ursula Martin pointed out this particular quote from Ada Lovelace's notes, where she says, "I have my hopes, and very distinct ones too, of one day getting cerebral phenomena such that I can put them into mathematical equations. In short, a law or laws for the mutual actions of the molecules of brain. I hope to bequeath to the generations a calculus of the nervous system." Unfortunately, Ada died quite young. She died at the tender age of 36 and never delivered on this aspiration. If she had lived a little bit longer and succeeded in these goals, then she'd have saved a lot of us a lot of time since. But possibly this was rather over-ambitious 200 years ago, and many would argue it's over-ambitious today. We shall see. To bring things a little bit closer to date, I live in Manchester. I work at the University of Manchester, and about 1.5 miles from where I live, south of Manchester, quite near Manchester Airport, there's this inconspicuous semi-detached house shown in the top left of this slide, and to the right of the house, to the left as you look at it, there's a brick archway with one of these blue plaques that you see almost everywhere about London, but they're rather rarer in rural Cheshire. And this plaque says, Alan Turing, 1912 to 1954, founder of computer science and cryptographer, whose work was key to breaking the wartime Enigma codes, lived and died here. While Turing was in Manchester, he worked on a number of issues. His fundamental contribution to computer science was before he moved to Manchester. He was at Cambridge in the 1930s. But while he was in Manchester, he did write one seminal paper, and that's the paper where I'm showing the front page on this slide, published in the journal Mind. And the paper's entitled Computing Machinery and Intelligence. And the paper begins the first section with these words: I propose to consider the question, can machines think? And then he went on to develop this theme, and he decided the question was not terribly well posed as a research question that could be answered. So he turned it around and cast it in the form of this thing which he called the imitation game, but which everybody since simply refers to as the Turing test for artificial intelligence. Of course, the imitation game is the title that Hollywood seized upon for its recent film about Alan Turing's life. This paper you have to remember that this paper was written 2 years after the world's first computer ran the world's first computer program in Manchester on June the 21st, 1948. So 2 years into computing, Turing was speculating this big question: can we build machines that emulate human intelligence capabilities? And Turing was reasonably happy, if you read this paper, that all that computers needed, compared with what they had then in Manchester and elsewhere, it was more memory. And he predicted that by the turn of the century, computers might have 1 gigabyte of memory. Again, this is a remarkable prediction for 2 years into computing. The Manchester machine had 128 bytes of memory originally, later expanded to 256. He was projecting 50 years into the future and suggesting 1 gigabyte might be possible. And if you think back, the turn of the century, it's roughly when your PC would have had 1 gigabyte of main memory. So he got that pretty close to right. He also felt that the Manchester baby was quite powerful enough, that more memory was all that it needed. in order for it to be programmed to replicate human intelligence. And at the turn of the century, the machines had the gigabyte. They were also 1 million times faster, and they still singularly failed to convincingly pass his test. And even today, no machine has convincingly passed the Turing test, although there was a debate a few months ago about a program that was run at the Royal Society. But the general consensus is that it didn't really pass the Turing test in the way that Turing intended. So building machines to display human intelligence has turned out much harder than Alan Turing imagined, and much harder than many people have thought. And my take on this, my personal view, is that the reason we found it so difficult to build machines that display artificial human-like intelligence is because we've never really worked out what natural human intelligence is to start off with. We don't understand how we ourselves do this thing we call intelligence. We have a very broad idea of what we mean when we use the word, but we do not know how it works biologically, and therefore it's proved very difficult to replicate it in machines. Now, just to give you a little bit more history and background, this is why Turing came to Manchester. Freddie Williams and Tom Kilburn led the development of the Manchester baby machine, which turned out to be the first machine in the world to run a computer program. Tom Kilburn, who formed the computer science department in Manchester where I now work, and after whom the Kilburn building is named, was very proud of the fact that in his life he only ever wrote one computer program, but it was the first one. He was really, like me, he was a hardware engineer. And they built this machine, not really because they wanted to build a computer at all. They built it because they'd worked during the Second World War on airborne radar, and they'd used cathode ray tubes to store analog signals to augment the capabilities of the radar systems. And they wondered if this same approach could be used to store digital information. Storage was the major problem in building computing machines at this time. And so they had this idea for digital cathode ray tube storage, and they needed to test it, so they needed a test rig that would read and write digital data very quickly. And the simplest thing they could think of to do this was basically a programmable computer, which, if you like, is an implementation of Alan Turing's big idea of the universal machine from the 1930s. So they built this machine, and Turing went to Manchester to use it. But let's just imagine this is representative of an early computer around the 1950s. Manchester has been building computers ever since. The most recent one I'm going to say a little bit more about later. This is a computer that forms a component in the Spinnaker system. The Spinnaker system will ultimately have 1 million of these computers. So they're now a component, but basically it's a very similar device to the thing that Williams and Kilburn built 63 years earlier. So if we look at those 63 years and compare those two machines, we can see the kind of progress that computing has enjoyed. Just over half a century, we've gone from machines such as the Baby, which used 3.5 kilowatts of electrical power, with which it would execute 700 instructions a second. And those two numbers tell you that it used about 5 joules per instruction. On the Spinnaker, we use a fairly typical, small, modern processor, the sort of which you'd find in your phone, not as the main processor, but in supporting roles, or in your digital music player or your camera. And this, the example on Spinnaker, uses 40 milliwatts of electrical power, with which it will execute some 200 million instructions per second. And those numbers can be combined to tell you that the number of joules per instruction is a very small number. And if you take the ratio of those two numbers, you get this measure of progress in the energy efficiency of computing, which on these numbers is a factor 25 billion over just over half a century. This is a formidable rate of progress, and it's one of the reasons why computers are now so ubiquitous, to the extent that in any room like this, the number of computers in the room always exceeds the number of people. You've probably got a dozen in your pocket somewhere if you have a smartphone. It's such a big number, it's quite hard to get your head around. One point of reference I like is I believe that the UK road transport fleet, all the cars, buses and lorries in the country, between them use about 50 billion litres of fuel a year. If the car industry had improved the energy efficiency of cars at the same rate that the energy efficiency of computers has improved, we'd be able to run the entire country on about 2 litres of fuel a year. The oil crisis would be billions of years into the future, and the world would be very different. Now, I'm enough of an engineer to know that there are fundamental thermodynamic reasons why it's harder to improve the energy efficiency of cars, though I'm still a bit surprised the car industry has only really started trying quite recently. But that's to illustrate just the scale of this progress. With this progress, we get the kind of machines that Turing could not have dreamt of. Now, before we get too excited about this progress in energy efficiency, I was challenged in a previous talk by somebody who said, well, if computers are so much more efficient, why is it that they're using more of the world's energy supply each year? And it's true, if you measure the total energy consumption of all the computers in the world, it's increasing, even though the efficiency of the machines is also increasing. And it turns out, and again, this was somebody in an audience of an earlier talk who helpfully pointed this out, this is a simple application of what's become known as Jevons Paradox. In the 19th century, Jevons noticed that Newcomen's relatively inefficient steam engines were being replaced by James Watt's much more efficient design. So the efficiency of steam engines was improving rapidly, and you might expect, therefore, coal consumption will go down. But actually, the opposite happened. Coal consumption increased. And when you think about this, the rationale is obvious. As the efficiency of steam engines or computers improves, their utility improves even faster. There are more things for which they're economically usable, and their utility grows faster than their efficiency, and therefore the product of the two gives you an increase in energy consumption. As an engineer, it's somewhat dispiriting to know that if I succeed in improving the energy efficiency of the things I engineer, they use more of the world's resources, but I can't think of any sensible answer to this. I believe, by the way, that if there are any economists in the audience, that Jevons Paradox is rather controversial and doesn't apply everywhere you might think it does, but it does particularly apply to technologies where the improvement in efficiency is primarily technological. Anyway, we now have all this computing resource. What are we going to do with it? And I've explained why I think artificial intelligence, in the strong sense, has proved difficult. And so the question arises, if we need to understand human intelligence first, can we use the computing resource that's now available to accelerate our understanding of that? And that basically means understanding how the brain works at the level of processing information. As a computer engineer, I'm also interested in the inverse question. As we understand more about the brain, can we use that knowledge to build more efficient computers? And this has led to this development of what are called neuromorphic technologies, trying to build computers that are tuned to this job of understanding how the brain does what it does to deliver what we understand as human intelligence. Now, neuromorphic technology, which I'm going to describe in a bit more detail, has attracted quite a lot of attention recently. A couple of years ago, the MIT Technology Review, which annually lists what it sees as 10 breakthrough technologies, decided that neuromorphic chips were one such breakthrough technology, and they were going to make computers far more astute about what's going on around about them. In an interesting parallel, the World Economic Forum listed its top 10 emerging technologies of 2015. And in their list, we find that we have neuromorphic technology appearing again. And if you look at the rest of their list, there are at least 3 other things where this technology has application. So in next generation robotics, emergent artificial intelligence, and sense and avoid drones, whatever they are. People who are doing reviews of global technology have decided this is an important technology looking forward. And several people are playing in this space now, not all of them just academics. So, for example, IBM has been putting quite a lot of work into the design of chips whose design is based on what we understand about the brain. And the IBM True North is a very impressive piece of silicon that they announced quite recently, which allows them to build models of millions of neurons on a single chip. And this works with very impressive energy efficiency. What you find in the neuromorphic space is there are many different approaches. And again, I don't really have time to compare and contrast these, but the ones I'm going to list are actually fundamentally different in how they approach a similar problem. Another academic group at Stanford has produced a design called the NeuroGrid. This is a group led by Corbet Naboahan, and they're building very energy efficient analog implementations of neurons, and they can get about 1 million neurons onto this circuit board. Our collaborators within the Human Brain Project at Heidelberg have another analog system. They're aiming to scale this up by building wafer scale silicon. So instead of dividing the 8-inch dinner plate, which comes out of the silicon fab, into lots of little chips, they're trying to use the whole plate at once. And that's an impressive technology. But the one I'm going to tell you about is the one that we're developing at Manchester, which is named Spinnaker, where Spinnaker is a sort of crude contraction of spiking neural network architecture. So it's not quite an acronym, and I always spell it with capital N's just to emphasize that it's about neural networks and not about yachting. The goal of the Spinnaker project from the outset has been to put a large amount of computing into a single machine, and the target has been 1 million mobile phone processors. Why 1 million? Well, it's a big number. It's about as big a number as you can sensibly plan to do on an academic research budget. And so it's a sort of trade-off between what you'd like to do and what you can afford to do. With 1 million mobile phone processors, just so you get the scale of the problem of trying to understand the human brain, with 1 million processors, you get to about 1% of the scale you would need to build a whole human brain model. And that's using really rather simplified models of the individual neurons, the brain cells that form the brain. 1% of the human brain doesn't sound like that much, so I sometimes prefer to think of this as 10-hole mice. Their brains are rather smaller, and one of the convenient features of nature is that you will find neurons used on every possible different scale. So C. elegans survives quite nicely with 300-odd neurons. Bees survive with just under 1 million. Mice have 100 million. Humans have 100 billion. It's a sort of, you can pick your animal to suit your scale. And to build the machine, we've had to adopt some design principles. One of the nice aspects of doing this work is it's quite popular with the media, and we had a big article in The Economist a couple of years ago, which means we get some great cartoons by Gorel. And here's one of the examples. This is The Economist's view of building neural chips. The principles we apply to building these chips are, firstly, brain cells come with all sorts of different connectivity structures. Different parts of the brain have different connectivity schemes, and it's very inconvenient to have to rewire computers for each new scheme. Indeed, if you go back to the early days of computers, before the Manchester machines had to be rewired to change their function, and the programmable machine was removing the rewiring. We do kind of the same trick in Spinnaker. We virtualize the topology so that you can map any neuron anywhere in the machine, and we'll logically connect them in the way that's required to build the model. The machine is a highly parallel machine with lots of processors. The thing that kills parallel machines is synchronization, so we don't do it. The machine runs asynchronously, and at every point in the machine, time models itself. And then thirdly, harking back to an earlier topic, the machine's designed to be as energy efficient as possible. And my view of computers today is that the hardware is now free, and the real cost of owning a computer is the energy you need to supply it. And this even applies to something such as a desktop PC. If you buy a basic desktop PC, work it hard for 2 or 3 years, you'll find you've spent more on the electricity to feed it than you paid for the machine to start off with. So the hardware is getting very cheap. We've designed the machine from the silicon upwards. Really, this is our engineering background. Our engineering heritage at Manchester is designing microchips. These are expensive and difficult things to design. This square centimetre of silicon represents about 40 man-years of design effort over a 5-year period. So there are a lot of work to design. One of my claims for this style of research is you get more PhDs to the square millimetre than most other subjects. We ended up with a chip a few years ago, and the chip is highly tuned to the problem. So if you look at what's on the chip, one of the mysteries to me, of course, is I've spent the last 30 years looking at pictures of chips and kind of being able to interpret them, and I have this feeling that for most of the population, it's just a sort of pretty piece of abstract art. But the chip is two-dimensional, so you can identify areas on it, and there are ARM processors in there somewhere. You can't find them. Even the experts can't spot where the processor is in these because it's been assembled by a computer, which means it has very little visible structure. But we've tuned the memories that we use for modeling the neurons and the memories that we use for modeling the synapses and so on. And the key innovation in this machine, the thing that makes it better at this problem than a conventional computer, is the way we implement the connectivity between the various processors. On Spinnaker, the brain cells, the neurons, are modeled by little bits of software running on these tiny cores. And when they communicate, neurons do this principally by spiking. They go ping every so often. All your thoughts, as you're sitting listening to me, are patterns of pings running around inside your head. And these pings we turn into packets in a packet switch network, a bit like Ethernet, if you're familiar with that, but much, much lighter weight. So that the packets are tiny and the routing is very lightweight. And that means that we can maintain real time, which in biological terms means everything has to be done with sort of sub-millisecond delays right across the machine. We can maintain real time across this million processor system, which is something you can't do even on the world's fastest computers today. If you get a high-end supercomputer, you can't do real-time spiking neural modeling above a certain scale because the communications is too heavy-duty. So that's the key innovation in Spinnaker, is the way the processors talk to each other. And neurons have lots of connections between them, which we implement in Spinnaker using a technique known as multicast routing, which means that whenever a neuron goes ping, that ping is conveyed across the machine to many targets. So there are many recipients of each ping. But we can't do it the simple way, which would be to broadcast all the pings everywhere, because then you'd have too much ping traffic and the machine would not be able to run at the required speed. So we just need the pings to go to the places where they're needed and nowhere else. And there's a particular approach we've used to delivering that that's based on associative memory that identifies where the packet should go. And to build the machine, because we don't expect our computational neuroscience customers to really want to worry themselves about real-time ARM code, we've built a stack of software that will take a high-level description of the brain region expressed in a language which the computational neuroscientists already use. These are languages with strange names such as Pine or Nengo or Nest. And then we build the tools that automatically map these networks onto the machine and decide where to put things onto the machine to make it all run. Now, scalability has been an emphasis from the outset. The million processor target was set to ensure that we forced scalability onto the system. And with 1 million processors, we can model the order of 1 billion neurons in real time. And the scaling is a matter of multiplying numbers together. So we get about 1,000 neurons on each ARM core, 18 cores on a chip, 48 chips on a board, 24 boards in a rack, and then 5 racks in a cabinet and 10 cabinets. And if you multiply those numbers together, you'll find magically the number creeps just past 1 million. To physically build the machine, these machines are not going to be small. So we can get about 1 million neurons on a basic circuit board, which is the size of an A4 sheet of paper. That has 864 processors on it. And to give you an idea of scale, it's roughly the scale, the network scale of a small insect brain, something such as Drosophila the fruit fly. I have to be quite careful when I say, I'm not saying, and you can model a fruit fly on this, okay? I'm being careful with my words because that upsets the neuroscientists, because there's lots we don't know about even Drosophila that you'd need to know to model the brain. But so I'm referring to the scale of system that you can model, rather than making a claim that you can actually model the animal. A rack that you can fit on a desk with 20,000 cores in is roughly the scale of a frog brain. The 19-inch rack cabinet on the right-hand side of this picture is 100,000 cores, and that's roughly the scale of a mouse brain, and 10 of those gives us the full-size machine. Now, because in Spinnaker, all the neural modeling and all the plasticity rules about how the networks learn are small bits of software, they're highly malleable. You can build different models. And what we find is that in the computational neuroscience community, almost every group has its favorite model, and they all have strange names. But because we're software, the magic of software is you can program it to do almost anything. There are constraints, but we have a lot of flexibility. So one of my students built a system which is based on a stochastic neural network developed by Wolfgang Maass. And this is a Sudoku solver. And what this is doing is solving Sudoku as a big parallel problem. And there are neurons which are giving the probability of a particular square being a particular number. As the network becomes more confident, the number gets brighter. And so it's all assessing this probabilistically. And even in its final state, as you see here, it's not as confident about some numbers as others. But earlier on, it had red numbers, and those were ones where its best guess was actually wrong. But fairly soon, the incorrect answers become so unlikely that they don't appear among the most likely set. The kind of things that we're expecting to do very soon in the future are exemplified by this network that Chris Elias-Smith's group has built at the University of Waterloo in Canada, and he's written a book, if you're interested in pursuing this, How to Build a Brain. I mean, it's a pretty direct title. And the brain, as shown on the right, rather graphically, is solving an intelligence test. This is an artificial neural network of 2.5 million neurons that is capable of demonstrating a reasonable number of different cognitive capabilities with the same network. So there's no network change between solving one problem and another. The problem it's doing here is of sequence prediction. And apparently this is a problem which, cast in a slightly different form, is something that you can train crows to solve. So this is about as far as we've got in training crows on intelligence tests. I don't think they write numbers the way this one does. But currently, this model runs in Waterloo on a fairly big cluster machine. And it takes 2 to 3 hours of computing to model each second of real time. And when we have this running on Spinnaker, we're confident it will just run in real time. And that gives interesting possibilities. For example, we can replace the virtual eye and the virtual robot arm by a physical eye and a physical robot arm, and we can interact with the machine much more directly. So that particular network is one of our early targets for big networks, and we expect to have that running within the next month or so. One of the issues here is if you build a machine to support big networks, you find there aren't many big networks out there because computers aren't capable of running them. So there's a chicken and egg problem. And we're creating the chicken. Is that the right analogy? I'm not sure. A bit closer to the data science interests, we've got boards out with a number of groups around the world now. And one of our boards is with Nick Kassaboff in the University of Auckland in New Zealand, which is about as far away as you can get. And he's interested in using these kind of neural networks as components in big data analysis systems. So you see here a block diagram of his system for analyzing spatiotemporal data, which has several components, one of which is a Spinnaker board. And the physical manifestation of this is shown here. The little board, the bare circuit board on the right is one of our small boards. And the kind of things he's doing with this is taking large data sets. Here's examples of brain data sets, which are very hard for humans to understand. And he uses neural networks to do dimensionality reduction, which then simplifies the data to the point where you can present it in a digestible form to a human viewer. This particular illustration is looking at the differences in measured brain activity between addicts and healthy subjects and addicts on methadone treatment and so on. And by processing this data, you can see differences in their brain dynamics. So that sort of concludes my introductory talk. I've been talking quite a lot about Spinnaker, which is the system we're building in Manchester. It's been 15 years in conception and 8 years in construction, but now it's built and ready to go. All it needs is some interesting challenges to address. We have boards out with about 40 different groups around the world. We built the 100,000 core machine. Interestingly, the million core machine is currently held up with internal university building issues. The university decided to close the data center where we were going to assemble the large machine, and it's currently spending money building a new little room for us to put it in. That'll be sorted soon. This machine is one of the several platforms that are being offered openly to a wide European audience through the Human Brain Project. HBP is basically setting out to provide infrastructure for brain science research across Europe and to try and encourage the various flavors of brain scientists to make more ambitious use of ICT. We are thinking, we don't have any good answers to this, about what you might do with a billion neuron system in the areas of big data and machine learning. One example is that we can run deep networks very easily on Spinnaker. We like to run spiking deep networks, and the standard deep networks that are used in conventional state-of-the-art machine learning are the non-spiking form, slightly old-fashioned neural networks. And the world has not yet quite worked out how to translate deep learning networks smoothly into spiking formats. But we believe that can be done.
Have a round of applause for Steve Furber. Yeah. Thank you, Dan. Steve, I just want to pick up on something you said. One of the reasons strong AI is so elusive is we don't really know what the I means yet, the intelligence means yet. That implies, though, once we do understand the brain better, strong AI is not far off. Is that correct?
Well, we don't know. I mean, that's the point. There's still quite a lot of controversy about how deeply you have to go into the biological system before you get the root of intelligence. Okay. So the models I've talked about are fairly simple Newtonian models where a neuron is a couple pair of differential equations and plasticity rules are similarly defined. There's a big debate, not particularly amongst the neuroscientists who are all fairly happy with that model, but if you read Roger Penrose's book on the Emperor's New Mind, he argues that you can't explain intelligence at that level, that you have to go down into some deeper, weird physics.
How hopeful are you that we'll get there quickly? I look at, and I was chatting with someone about this, the speed with which we got to soft AI, self-driving cars, vacuum cleaners that clean up the rooms themselves. Bearing that in mind, does that make you hopeful that we'll get to strong AI sooner, or quickly?
I think I'm reasonably optimistic that we will get to the root of the processes that underpin human intelligence on the timescale of a decade or two. Now, you will find many people who disagree with that very strongly. They think the problem's much harder. I tend to be, in research, I tend to be an optimist. I think most problems, if you believe they're as hard as they can be, you'd never start. So I think you have to start off optimistic and then...
Good. Well, and back to something else you were talking about, the million processors. That's all you get, you say, on an academic research budget. But there are, and this is something you and I discussed on the phone a couple of days ago, there are, governments are investing a lot of money into this space, but the private sector is investing a lot of money into this space. Why is a million processors why can we not throw in another 10 million?
Well, we could. The machine I built was not that expensive. It could be made a lot larger on a tiny fraction of a defense budget, for instance. But we don't know what we're doing. And in some sense, you can only justify spending so much on research when you don't know what you're doing, I think.
When do you know, or when do you realize that you do know what you're doing? What tells you that? What's that moment when you think, yeah, we actually do know what we're doing now?
It's the essence of research that you don't know what you're doing in some sense. If you knew what you were doing, it would be development. I I think we'll know what we're doing when we can produce models that replicate observable phenomena. That's one of the really hard problems in neuroscience is if you model a part of the brain, you start with a black box whose internals you don't know, and you don't know what its inputs are, and you don't know what its outputs are. So it's quite hard to say when your model is doing the right thing. Now, of course, people try and find specific models where there is more known about the environment, but it is quite hard. And one of my views is that the difficulty with small-scale computational neuroscience modeling are those difficulties, and they reduce as you increase the scale. And when you get to something that's modeling a whole animal brain, then you can expect, you can see animal behavior. And if you can replicate aspects of behavior, then you're getting somewhere, I think.
You've said, two parts of this for you. First, understanding how the brain works, then using that understanding to make better machines. So I don't want to draw you too much into this, the existential worries of the doom mongers. What was it, Elon Musk? What did he say? A demon that foolish scientists are summoning, I think is a quote from Elon Musk. What do you make of those worries of the doom mongers? Are they justified?
Well, some of the doom mongers are sort of motivated by this concept of the singularity, which is the idea that as machines gain in intelligence, then they will be able to out-design us and build better machines, and the intelligence of machines will grow exponentially, or some very high gain function. My complaint or my argument with that is that I'm not at all convinced that intelligence is a simple physical quantity that can be amplified. Okay, I think intelligence is we don't know what it is, all right, but I think it's far more subtle than that. And if you imagine that you had a hyper-intelligent machine, what would it do? Okay, what would be the sign that it was more intelligent than us? Would it find the political solution to problems in the Middle East? It's hard to imagine that would emerge from this kind of intelligence.
So these guys, the Elon Musk, and let's face it, Stephen Hawking, throw him in there as well, they need to calm down a little bit about it.
I think they need to calm down. Okay. And it's clear that human intelligence is manifest in many different forms. It's not just an ability to do hard maths or play chess well. I mean, there's some form of intelligence involved in being able to kick a leather ball off a spot into the back of a net, right? Indeed, as far as current evidence goes, that's the form of intelligence most valued by human society. But it is a form of intelligence, right? It's not something I can do. Right. And yet it's quite different from the kind of things I can do, which demand a different sort of intelligence. Yeah. So I don't think intelligence is a simple scalar that can be amplified.
And you've got two great teams from where you come from, right?
Sorry?
You've got two great football teams from where you come from.
Well, it depends who you ask.
Actually, to the point, I particularly like the quote, and this came from Nicholas Carr. It was a piece he wrote in the New York Times. If computers had the ability to be amazed, they'd be amazed by humans. I like that. It sort of sums it up quite well for me there. There are so many other things I want to ask you, but I've got a wary eye on the time, and maybe I'll have a chance to come back to a couple of them. But let's have some questions from the audience.
Why are we focusing on creating such an enormous computational machine without knowing what the computational model that's going to go in it is going to be?
So I think I see what you're getting at. I mean, the fact that the machine works by solving equations is kind of second order. The key thing about the machine is it's able to support systems of very large numbers of simple interacting processes, okay, which is a fairly straightforward description of how the brain appears to operate. I mean, neurons have a certain degree of sophistication, but the creatures with small numbers of neurons are only capable of fairly simple behaviors. Why are we building a machine to understand the brain is probably the nub of the question. And I think there are a number of answers to that, of which the first simple one is scientific curiosity. Usually, if we don't know something, we try and find out. And we don't know how the brain processes information, so that's worthy of scientific pursuit. Perhaps more economically significant is that if you look at research into treatments for the various forms of brain malfunction, brain diseases, largely that's stopped because of the lack of a model to use for developing the treatments. So the big pharma companies have largely stopped investing in drugs that might help brain disease, and brain disease is economically more significant to the developed economies than cancer, heart disease, and diabetes put together, okay, in terms of its economic cost. So there's lots of good reasons for wanting to understand enough about the brain to be able to develop treatments and therapies that might alleviate that cost. And of course, economic cost is one way of measuring it, but the quality of life impact of brain diseases is anything far more significant to those affected.
Okay, thank you very much. Let's have another question. Yeah, right here.
I'm fascinated by the operating systems that are going alongside the research that you're doing, because clearly it's the operating systems that will determine the actions in some ways.
Okay, yes, so you're right. My talk does betray the fact that I'm a transistor hacker by heart. And you know, given any particular impressive piece of computer performance, I say, how many transistors does that take? And other people have different angles on this. So I mentioned a little bit about the software, the fact we have a software stack that maps things onto the machine. Because the processors we're using are really quite small. I mean, these are you know, the smaller processors you'd find in your phone, not the big one. And I suppose that the number I should frighten you with is the fact that each of these processors has 32 kilobytes of code space, which tells you something about the operating system. It isn't Windows. Although, you know, today's undergraduate comes in and you say, here's a machine, it's got 32 kilobytes of code space, go and make it do something spectacular. And they say, how can you possibly do something in 32 kilobytes? At this point, I get out my trusty BBC Micro and show them what David Braben did with Elite in less than 32 kilobytes. You know, it's actually quite a lot of resource, even though by today's standards it's tiny. We have a slightly unusual software model, so the system is entirely real-time, event-driven at the operating system level. Each of our chips has 18 cores on, 16 of those run the application code, and a 17th runs operating system stuff, so it's dedicated to kind of looking after the others and monitoring, and the 18th is a fault-tolerant spare. We now have more people working on the software than we have on the hardware. Partly that's because it's at least as big a problem, and it's partly because we don't understand it as well.
You know, the company DeepMind that Google bought for a lot of money is focusing on the problem of teaching computers to learn themselves. So rather than training them, teaching them how to learn, so how to learn to play chess or how to learn to play Space Invaders. Yep. How does what you're doing fit into that kind of model?
Well, I don't know the details of the DeepMind model. The stuff they're doing, I think, is very interesting in terms of getting systems to learn autonomously. They do it in a conventional programmed environment. A lot of the work that we see being done in neural networks has a similar angle. I mean, you can't train large neural networks to perform all their functions. They have to do some autonomous analysis of inputs. They have to, what's the right word? They have to be able to do unsupervised learning quite extensively, which is usually expressed in terms of learning the statistics of the inputs they're presented with, and they have to do that autonomously. And quite a lot of the neural networks research is in that space. It's not as advanced as the DeepMind stuff is functionally, but it's more biological. And so DeepMind is a very interesting general artificial intelligence system, but it doesn't necessarily tell you anything about how the brain works. It doesn't solve the problem that we're looking at, which is understanding how the brain does this, which we see as the first step to getting really powerful AI systems. But it also has many other outcomes.
And maybe that's what scares people, that this is doing what it's doing and it's not actually trying to understand how the brain works. Is that part of the fear that some people see in AI and strong AI?
I think people fear AI because it feels like unfair competition. I think machines have replaced quite a lot of human jobs, and if machines become more intelligent, they'll sort of move up the human job ladder.
And humans will go the same way as horses, is what was written after. I'm sure I read a piece about that. Will humans go the same way as horses after the Industrial Revolution? But
well, that's yes.
McAfee, actually, I think was authored that. Yeah.
I'd like to start by, I come from the Middle East, and I think as big as the machine can be, the problem will not be solved. But today, the human brain is trying to put up a machine together, to think, and to try to see actually how the human brain works. And if this works, it goes without saying that it's the machine that's going to outsmart the human brain, and that the human brain cannot judge that. But how can we trust that the output is actually true, since it's bigger than what we can think?
Well, I think I would debate your premise. Okay. Firstly, were you referring specifically about the European Human Brain Project, which is primarily about building an infrastructure for brain research, with, of course, the ultimate long-term goal of understanding how the brain works? But the primary activities of the project are to do with building that infrastructure such as Spinnaker. I mean, Spinnaker is not going to tell you how the brain works, but it's a machine that can be used to test hypotheses that people generate about aspects of brain function. Even in the limit, if we fully understand how the human brain generates human intelligence and we can replicate it in a machine, it's not at all clear to me that the machine will be brighter, it'll be any cleverer. Okay. We're really struggling to get it. We're really struggling to get machines that can come anywhere close to fruit fly in terms of intelligence. As we understand more, we will progress up. But I think saying we can get to human intelligence is very different from saying we can get way beyond it. The other thing that's worth pointing out is that on the best estimates, the compute power you'd need to run a real-time model of the human brain would be bigger than the world's biggest supercomputer today, which is Tianhe 2 in China. It's about an exascale machine on the best estimates, and there are doubts about that. We are really struggling to work out how to build an exascale machine that A, isn't bigger than an aircraft hangar, and B, consumes hundreds of megawatts of electricity. Okay. So it's a very, very poor substitute for a biological brain. Biological brains fit neatly inside your skull and run on about 25 watts. So the point of investing in a massive machine that can replicate it is not to replace it. It's just a very poor way. It's nowhere near the efficiency of the real thing. But it's much easier to inspect. It's quite difficult to ask questions about what's happening inside a human brain, even if you overcome the ethical issues of being allowed to stick probes in. Sticking probes in brains is extremely demanding and very difficult to interpret the results. Whereas once you have a computer model, it's very easy to interrogate it and ask what's happening in different places. So as a tool for understanding, it's justified. As a replacement, I think it's a non-starter.
As you previously said, the concept of intelligence is much more difficult to define, and maybe here it seems that we didn't talk about the chemistry that might be more difficult to replicate, to build a brain which can understand also through emotions or other aspects. So I was wondering, what's your trust on the research on the nanoscale level of the actual brain and the quantum effects that can maybe be the basis of some information regarding the nonlinearity of the brain or the genetics of the brain, and how do you think that can be useful?
There's lots of underpinning biology that's a great interest to neuroscientists who want to understand cells and ion channels and genetics and so on, that we completely ignore. And what we're trying to do is the well-established process of abstraction, which is to say, let's not worry about the details of the ion channels and the genes and the biochemistry. Let's try and look at the function. Let's try and capture the function. And if we can capture the function, and we can capture how information is represented and how it flows, then we can abstract all that stuff away. I mean, I can build an ARM processor using transistors. I could build it using fluid logic gates. I could build it out of electromechanical relays. The implementation technology is immaterial when it comes to understanding the microchip at the level at which it performs its logical function. And the hope is that something similar is true of the biology. Now, of course, the reason it's true of human-engineered systems is they're very carefully designed to do that, because we have very limited capacity to understand complexity. So we use abstraction as a way of removing complexity layer after layer. And you know, if you go through a computer science course, you'll be presented with the abstractions that operate in computing systems at about 10 or 12 different layers. And each layer of abstraction completely hides everything that's happening underneath. And in engineered systems, you can design them to make those abstractions very sound. Biology, of course, hasn't been designed in the same way. It's developed in ways that means it often cheats. It often breaks abstraction rules to achieve function. But even so, if we want to understand something as complex as the brain, we have to hope that there are valid abstractions. If we really have to go down to the cellular biochemistry in every neuron in the brain, then we're sunk for centuries. So you see, again, this is researcher optimism. You have to believe this is a tractable problem. If things like quantum effects in microtubules are really important, then we're on the hiding to nothing.
Thank you very much to everyone who did ask a question. Thank you very much for coming along this afternoon. It was a fantastic talk from Steve. Thank you very much indeed, Steve. Steve Furber.